Hello everyone, welcome to this video. In this video, we'll be solving this question which states that prove that for every subgroup of Dn, either every member of the subgroup is a rotation or exactly half of the members are rotations. So here we have to show this thing. So if you remember, what is this group Dn? Dn forms the group of symmetries of an n-sided regular polygon, right? We study its symmetries, right? Now, you know there are exactly n reflections for this Dn, and there are exactly n rotations for Dn. This thing we already know, right? Now what we are doing from this group Dn, we are taking out a subgroup, right? Which we are calling by H. Now for this subgroup, we have to tell that either all the members are rotations or exactly half of the members are rotations, right? The case that is not possible here is that all the members are reflections. Why? Because you would definitely have the identity element with you, which is R0, which is rotation by 0 degree, correct? So therefore that case is not possible, right? So now let's consider this thing over here. We assume that HB are subgroup, right? In the first case, we say if every member of this subgroup is a rotation, then we have nothing to prove. Our result is proved in this case, right? So in the first case, our result is proved if every member of this is a rotation. In the second case, we assume that every member of H is not a rotation. So there would at least be one element which is not a rotation. Suppose we call that element as F1, which is not a rotation. Hence, it must be a reflection, right? Now, we have to show that if there are m rotations present within this subgroup H, R1, R2, R3, R4 up to Rm, then we have to show there are exactly how many is reflections possible. There are also m reflections present here. So they are equal in number. This thing we have to show here, right? So if you know that whenever we compose a rotation with a reflection, you first of all rotate the figure and then you take its reflection, the answer would be a reflection, right? It would be some another reflection, but it would be a reflection. So therefore, if we are taking the reflection as F1, right, and we are taking the rotations R1, R2, R3 up to Rm. So this R1 composed with F1, R2 composed with F1, Rm composed with F1, they all would also be reflections, right? So if that is the case, they are all distinct and only we have these many of them and there are no other reflections, then we are done because they are also m in number, right? So in order to prove this, we assume that apart from these m, we also have some other reflection. Let's call that by f dash, right? If f dash is any other reflection in K, then this two reflections would give you some rotation, right? This is also one result. If you apply, suppose in case of square, if you apply this reflection here, so this portion goes here, this goes here, this goes here, this goes here. Again, you apply the reflection that this goes here, this goes here, this goes here, this comes here, right? In that case, what you would have, you would have your result as rotated figure, right? Okay. So here your f dash f would be some rotation Ri. So what we can do, we can post multiply both sides with f inverse, right? So that this thing would become R0. R0 into something is that something only f dash. So you have f dash is equals to Ri f inverse. And you know the inverse of any reflection is itself. So in this case, you can write this f inverse as f only. So therefore, you obtain f dash is equals to RIF, right? And you had f dash f is equals to Ri. So that means corresponding to each reflection which we have taken to be some other reflection apart from those given above, we ultimately found that it is also of this form, right? So that means if you take any other reflection, so it would be present within this set only. Hence in this case, we conclude that there are only these m reflections which are present within this subgroup H, right? So therefore, corresponding to each reflection f dash here, it corresponds to some RIF, right? So therefore, whatever is the number of rotations we have with us, the same number of reflections would be present with us. And hence, we prove that every subgroup of Dn, because H was an arbitrary subgroup, so every subgroup of Dn, it contains either all the rotations or exactly half of the rotations, right? And this is what we wanted to prove here. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.